Testing. Sound to fluid, and okay, it's on. Okay. Check if it works. Yes. Mm-hmm. Third and final lecture. Yeah. Okay. Good. So let me remind you that it will be free books given at the end of this lecture for those who ask best questions. And the competition is open already. We had 2 lectures. We have some list, but you can participate and you have chances. This is the shortest. This is the shortest book on fluid mechanics as a way of advertisement, I may say. And it's written by physicists for physicists, because fluid mechanics, yes.
How do you evaluate questions?
How I do evaluate questions? I have a very simple algorithm, and it always works perfectly, whether I like it or not. And you may ask why I like it. I like it when you teach, when the question you ask, teach some other people about something. And sometimes it could be that you ask question and many people answer say, yeah, I also wanted to ask this. Yeah, I thought that everybody knows it. And you just let them know that not everybody knows it. This is because you learn from each other more than you learn from me. Just, you know, be active. Okay, so let me remind where do we stand, and we're doing pretty simple things. So I'm trying to tell you the way that physicists looked at fluid mechanics, and generally I avoid telling recent things, particularly my own recent works, because there is this rule, which is called tau rule. If you want to include everything until time t minus tau, when t is you're speaking, and tau, when it was t minus tau, it was published, it will be obsolete at the time t plus tau. So it's, but just for coincidence, today, in Today Nature, July 7th issue, came out our paper, it's an experimental paper, where the first observation of vortices in electronic fluid, which really makes it kind of truly across the scales. We now have really tiny electrons collectively flowing and demonstrating. And there is a, of course, mostly beautiful experimental effort, which is not mine, but it is Eldav's group at Weizmann. But there is also some kind of a non-trivial theory done, which we did with Levitov from MIT, about how actually you can derive viscosity for such microscopic system, and what electrons break Ohm's law and flow like a fluid. So with this aside, let me remind where we stand. So what we ended, we derived Navier-Stokes equation, which was earlier equation with extra term. And this extra term looks as a diffusion of velocity, right? So velocity is a vector, and you know, when you forget all this, you just dvdt is nu Laplace v, it's a diffusion of momentum, and we say that some molecular or electronic or whatever microscopic motion leads to the diffusion of momentum. And then we said we estimated for a gas that this diffusivity of momentum, and diffusivity is always some velocity times some scale, right? Diffusivity is centimeter square per second, right? Diffusion law is r squared equal to diffusivity times t. So diffusivity always centimeter square divided by second. So it is in this particular case, whatever velocity in the medium you have, for electrons there would be V Fermi, L mean free path. But generally it's just VL, whatever velocity, it could be thermal velocity of gas, it could be Fermi velocity of electrons. Now, what would be a natural question for a physicist to ask? It looks like gradient expansion. I mean, if you look at this paper, how we derive viscosity, you write kinetic equation for probability distribution function, or in the velocity, it's kinetics, for all the velocities at space r at time t, and you take some v particles now, not velocity of a fluid, times f, some collision integral, some external forces, and then you solve it. And of course, when you try to write equation for v, we should be you integrate over v and average over all v, because it's the probability of having velocity v, you multiply it by v, you get this v, which is a mean velocity of your element of a gas. That would give you this term, and the viscosity comes out of collision integral, right? This collision of molecules, which actually spread momentum. So it all looks like gradient expansion. So you may ask, why this term is not small uniformly, right? It looks like, remember we started from earlier equation, which was a decent thing to do. Just momentum transports itself, and pressure describes exchange of momentum between different fluid particles. Now on top of it, we also did this diffusion. And so we mentioned that if you want to really know how important this term relatively, for example, to this, which is inertia, well, as a physicist always do, we have two quantities, we divide one by another, we get dimensionless number, and we think that we're doing science at this moment, which science usually starts at this point. So if we take this term, we can estimate at some typical velocity squared divided by some typical scale. That's a nonlinear term. And if we divide it by this term, which we say that it is nu, and here it is u, and here it is r squared, this dimensionless number is called a Reynolds number, and it's apparently u r over nu. Let's now plug here this nu, which we just derived, estimate, okay? And this would be u over v thermal, L over R. Now, this indeed is very, R over L. R over L. So I took this and put it in the denominator. So indeed, yes. What do you mean minus? Yeah, well, it's kinetic equation. Okay, I'm not doing kinetic. I just mentioned it poetically, so I can choose factors the way I like. Well, really, I want to call your attention that, of course, fluid mechanics is done when this factor is huge. That's assumed. Whatever molecular scale you have, electronic scale or bacterial scale, or whatever, where this microscopic exchange of momentum and diffusion of it happens, we all understand diffusion happens on a scale much larger than what real elementary processes happen. So this is huge. But Reynolds number could be both small and large, depending on whether your velocity comparing to the internal velocity. For example, V Fermi for electrons is 10 to 5 meters per second. For gases, it's strongly dependent on temperature. This quantity is square root of temperature divided by mass, right? Essentially, it's all is of order of speed of sound in gases. Thermal velocity is of order of speed of sound. So this is essentially your Mach number, if you wish, okay? So you see that this could be small or large comparing to this. That's why fluid mechanics really deals with very low Reynolds number when this factor overcomes this. Yes, Brad?
So if R is small compared to L, you're really in a ballistic regime.
When R is small comparing to L, you are in a ballistic regime totally. Even when R is like 100 L, you already, well, of course, in graphene, we of course kind of use it when R is like 10 L. But this is a stretching. It's normally a few orders of magnitude until you safely can use hydrodynamic assumption, because you need coarse graining, right? So you coarse grain over this scale. Otherwise, all this does not make sense. Averaging over kinetics makes sense only if you have several things. So this is really, I want this, what you remember, this is very simple things. And surprisingly, many people who do many things about fluid mechanics and use Reynolds number for many years, and particularly our graduate students, the question is that why you can use Reynolds number in the regime where Reynolds number is very small, if this factor is so huge and so large, it's because this could be small, right? So that's essentially the reason. The moment you approach speed of sound, even 1/5 of it, it's always something which means that you cannot really treat it in the way that you may treat low Reynolds number fluid mechanics. Okay, good. So I really want you to remember this simple thing. So now, if we are allowed to have low Reynolds and large Reynolds, even though most of my lectures is about large Reynolds, I really wanted to tell you something about small Reynolds, because you remember that essentially what is our main thing, it's about what is a force acting on a body moving with a velocity u having the size of r, and as Newton over 300 years ago claims that is some factor rho u squared r squared. And this is something which is assumed to work in the limit of very large Reynolds number. And what I've told you in the last lecture is that I don't know any other way to get this, to start from the limit of very low Reynolds number and then start slowly moving towards Reynolds number and discovering many things in the process until we end at a very large number with this answer, which is essentially the first anomaly in physics. And I was asked a very good question during the break, what is the anomaly? So let me repeat again what is the anomaly. You have a symmetry breaking factor. For example, your left is a little bit different from your right. You close your eyes, you start walking, you will be deflected to the left. Now you're training, you're getting yourself more and more symmetric. And so you ask whether the angle in which you walk blind-sighted goes to 0 when your symmetry goes to perfect. Anomaly means no. Even when you, however small imbalance would create a finite angle on average, let's say. So the same here, however small viscosity creates finite rate of dissipation. That's what we call dissipative anomaly. It's the main subject of today's lecture, but we start slowly at a very low Reynolds number. Yes, Leo.
This example, it could be a positive angle or negative angle.
It's a very good question, but it depends what is skewed to the left. You can be skewed to the left this way, you can skew to the... Yeah. And of course, again, as already clear by this excellent question, but you won't get a book, yeah? You don't come, is that everything about taking limit is about order of taking limits. So, and this is a huge branch of mathematics, which we'll probably happily skip. Okay, let's go to low Reynolds number, okay? So now if we go to low Reynolds number, not only we can drop the second term, and we can also drop the first term. Because again, low Reynolds number means nu going to infinity. And as Julia already told you many times, it means instant diffusion of momentum all over the space. It's infinitely strong diffusion. So essentially what you're left with a Stokes equation, again written by a guy in his PhD. So if there are PhD students, it's still, so you get essentially nu Laplace V equal to, or I would put it eta, and eta is nu times rho. It's called Stokes equation. It's linear. It's surprisingly non-trivial. Surprisingly. Yeah. Yeah, it does not. It does not. It has infinite viscosity. in a sense, what you actually claim, you claim that your Reynolds number is very small, which means that this is very small. Let's say I have a body, okay? And it moves with a velocity u. Thank you, Julie. You also won't get a book, but it's a very helpful question. Let's say it moves with this u and it has this r. And I stop pushing it. How fast it would stop? How much time it would take to stop? It would take time that its momentum takes to diffuse away from the body because the fluid takes its momentum and then it stops. What is the diffusion time on a scale r? If you have a diffusivity nu, the time of diffusion is, of course, who said it? Good. I'm totally I'm Russian. I have no principles, okay? But I'm not yet giving book. We're in a competition. But you have a good shot, okay? That's how much time it takes to stop it. How distance it would travel during this time? Well, the distance would be r. This time velocity, okay? So this distance that it would travel would be r, ur times nu, r times rate. So that's what we mean by instant, okay? Which means that whatever you stop pushing, it stops on a scale which is much less than its size. That's essentially the statement that low Reynolds number is a regime of very low diffusion. Now we may estimate what force, resistance force would act on such a body when we continue pushing it. How much force we need to push it with a velocity u. So of course this force now, there is no pressure, right? So we need to integrate now not a gradient of pressure over the surface of the body, we need to integrate tangential stress tensor. You remember we call it sigma. And of course, we know how to estimate. It's eta grad V. Remember from the last lecture that the tangential stress tensor in the Newtonian fluid, assuming low gradients, etc., this is momentum flux or stress tensor. So this is something which is eta u divided by r. And this is just area. We estimate it as 4 pi r squared. And we get the formula, which is this ubiquitous PhD student Stokes derive. We get a Stokes formula. Of course, Stokes had 6 here, but see how close we are to exact derivation. This factor 3/2. I wish all my theories was as good. So it's 4 pi u r eta. So now, if we say, okay, I'm interested in engineers prefer this and physicists how inherited it. So I would plot C, which is force divided by its Newtonian estimate as a function of Reynolds number. So what Stokes tells me? It tells me that this force, or the C, is proportional to viscosity. And because Reynolds number is 1 over viscosity, then it's like this, okay? That's a Stokes law. It's a dimensionless number, it's 1 over f, okay? So now, if we would live in a non-anomalous world, which some people read, and we would expect this just to go as my viscosity goes to 0, to go to 0. And what Newton claimed is that it comes to a constant, this constant which is shape dependent, but of course needle and disk would have different constants, they have different shapes, but generally so for the unit, okay? So now how to get from here to here, we already discussed. I'm kind of repeating part of my path. It's a boundary layer separation, okay? So let me again remind you, what is it? Because maybe I'll just, for symmetry, would go to the other side, so you people here won't feel abandoned. So let me remind you now what we expect to have. So what actually Stokes regime, this low Reynolds number regime means, it means that if we define a typical scale where this term V grad V is getting of order of Laplacian, because we would need to solve the U around, and Julia have shown you this Stokes solution, which is 1 over R. It's actually an important which way of decay, but you will discover that there is always a scale which is nu over U, where viscosity is comparable to advection. And what is actually Reynolds number means, low Reynolds number, which means that U R over nu much less than unity, it means that R, your size of the body, is much less than nu over U, which is the size of a boundary layer. So in a sense, Stokes regime, there is not a boundary layer. It's a huge viscous region, which is much larger than your body. Now let's start decreasing viscosity and shrink the boundary layer. We shrink, in the limit of large Reynolds number. So when we take Reynolds number much larger than unity, it's the same as saying that your size of the body is much larger than the boundary layer. And here Prandtl comes, 1905. So what Prandtl considered, he said again, let's look at the flow, let's take a symmetric flow. It's essentially not that important, but for the sake of an argument. Let's take a cylinder or a sphere in its projection, and Reynolds number is very large, which means that whatever boundary layer is very tiny. But let's consider such a fluid particles which come very close to the stagnation point, which is on the symmetry axis. And that particle must enter boundary layer, because it would then follow very closely to the surface, right? And what we discussed is that this is stagnation point, velocity nearby is low, pressure high. This is the maximal velocity point. You need to go around all this. So this is pressure low by this Bernoulli relation, which we derived in the first lecture. Okay. So what particle does over here, it is pushed from behind by a very high pressure and accelerates towards this low pressure region. Totally legitimate and easily understood process. What it needs to do on its way back is to come to a symmetric high pressure region, overcoming the adverse gradient acting on it. And if this fluid particle happen to flow outside boundary layer, it could easily do it because there is no friction. But if it's in this very tiny region, there is a friction. And when you're in a friction, you diffuse your momentum away. It goes out of the boundary layer. Okay, so you lose your momentum. Diffusion is viscosity is a diffusion of this momentum in that direction. It's a kind of vectorial diffusion, right? Not a scalar quantity which diffuses by a vector. So what, as a result of it, it cannot come all the way here. And at some point, it deflects. And because it's a continuous motion, if it moves like here and it moves like here, then what we realize, what appears is a recirculating vortex like this, and a symmetric to it vortex like this. And this is called separation. And illustrious German mathematician in Göttingen, which never had engineer, with their dirty hands crossing this building, took this young guy who was an engineer, and the talk was given in the meeting of engineers, and immediately made him professor of mathematics in the most illustrious place in German academy, because they immediately understood what this simple hand-waving argument means for mathematics, first of all. It was kind of a birth of a real physical application of singular perturbation, of symmetry breaking, of which we most 20th century we spent on it. It's a really illustrious achievement. And the fact that what we discussed with Shin is that he did not get Nobel Prize for it is just, well, there are people to blame. So this was this idea of separation. And now it starts to explain why you can have a finite resistance when viscosity goes to zero. When viscosity goes to zero, this width of a boundary layer shrinks and shrinks and shrinks. But the point where it separates eventually stabilizes. Okay? What is important, and this is something which as a physicist you really must appreciate, that the wake is infinite. Right? If it would kind of die out eventually, because okay, that's my new body. That's my new body. I do theory, and like we've seen last time, for arbitrary shape, we would get a zero resistance for a constant motion. What is important is that the wake is infinite. And then you are trying to say, okay, then how I compute this resistance, the force of resistance? Of course, you need to take, let's say, this would be X, this would be Y, and this would be Z. I don't know if it's visible there, but, and let's say we really want to compute whatever Fi we want to compute, we need to integrate exactly like we did for Stokes, but we just need to take the whole momentum flux and integrate it. And let's say we do it taking all this huge enclosure, but wake coming through it. So I'm taking a surface around my body, but what I do know is that there is always a region in this surface where I cannot treat my flow as an ideal. What is here in this region, which is infinite? The particle who came close to this point. What is so different between particles here, this is called wake, and outside, is that this particle has zero vorticity. This flow, which came from here, was a uniform flow. As long as it did not enter boundary layer, it felt practically no viscosity. Practically no viscosity, there was Kelvin's theorem, which was saying that here, curl of V is zero, but not here. All the particle here now pass through this boundary layer where you have this type of flow. That's vorticity. dvx over dy, that's vorticity, okay? So what we have is a wake where our potential flow assumption is unimportant. It's not true, which means that even though particles here don't feel viscosity anymore, right? They already passed through their viscous unhappy period of life. It was relatively short, but they acquired vorticity forever. It's a curious resemblance to superconductors and superfluids where we have all these vortices coming out, right? So in general, I mean, like flow is, you have Meissner's theorem for superconductors, right? But no, there are always this vorticity, which makes life so fascinating and got so many Nobel Prizes for condensed matter people, that there is a vorticity coming from. The same here, there is vorticity coming from common region and staying forever, okay? Now, if we would like to estimate it, even using, let's say we are far away, we forget about viscous stress tensor because it's really small, viscosity is very small. So we would have here, it is this, P would be, you remember the earlier expression, and let me write velocity like U plus V. And V would be, this is U, oncoming velocity, and it's a mean average velocity of a flow, and V would be a perturbation. So there will be terms like rho UI plus VI, UK plus VK. And you need to integrate all this over DFK. There is no viscosity here. What I'm now doing, I'm saying, if I take an enclosure very far from a body, I can totally neglect viscous forces. There is no viscosity now. And so what I'm trying to illustrate is how you get now a non-zero answer not out of viscous stresses like it did, but from the fact that part of your flow now is not irrotational. That's anomaly. You don't need viscosity. It does not matter here. Yes, Julia? We,
How do you go zero Reynolds number up to?
in 5 minutes. It's excellent question. This is precisely what we're going to do. It's a typical way of I don't know, my way of doing. I never follow logic, which means that I told you something about zero Reynolds now. Now I'm telling you some infinite Reynolds number, and then I try to connect one to another, walking you through all the transition of the flow when you go from Stokes flow to wake flow. It's not a trivial role. Okay? Yes.
Just to be clear, this is the integral you did for us before it got zero. Before.
Absolutely. Now,
They assume the rotation.
there I assume a retention flow. What I now want to illustrate is that out of this guy, which you can happily plug here, potential flow around the sphere or any body of any shape, because you're doing it very far away, and far away it does not what the shape of the body, right? Any body looks like a point from long distance. So potential will give you zero. So it's clear that we'll now get an answer which will be due to this. Yeah, this our surface passes through wake somewhere. So now you can see that, of course, everything which is independent on V would be zero. This is just constant. Quadratic term VI, VK also will be unimportant because an integral of VK dfk is zero, it's just a conservation of mass inside, right? So what you find out is, something fallen, that force, let's say X force would be rho u, this is just a constant, integral over dy dz of v x, of perturbation. And this integral over the wake cross-section, right? This is what you really get is that only here in this cross-section you cannot, and that would be your result. So this is essentially clear, very clear physical meaning of it. It's a deficit. This is a perturbation of V with respect to uniform flow. This is because you have your body and it created this wake, it makes its velocity a little bit less there. We don't know how much. It's something which depends on X and Y and Z, and it definitely decays with the distance. But it's force. It's independent on where I decide to put my thing. Yes, Aaron?
You have, in the Bernoulli principle, when you had key height of the same on both sides.
Yeah.
Why should I expect that to be true? Why can't the energy be lost at a slightly lower pressure?
Bad question. I won't answer it because it would take like 10 minutes, and you can find. This really, you need to find Bernoulli's theorem because pressure is not pressure, it's pressure plus variation. Variation is expressed through V. I won't go there. And you just look into the book, which you have chance of getting, and then you can see it. But what I'm saying, on the other hand, the answer is quite natural. I mean, I did not derive it, I kind of hand wave into it, but it's kind of natural. Of course, this must be rho V squared R squared, right? Like Newton wanted. So it's a squared velocity, but it's interestingly squared velocity. It's U times perturbation. The most amazing part here, which I really want you to appreciate, the most dramatic part here, is not even how this decays with the distance. It depends on how wake widens with the distance, and in a moment we'll derive it if we'll have time. It's the statement that this is independent on a position where I decide to take my surface, because it's a force. It's what? Let's try to think why it's such a dramatic statement. It tells me the following, that you take a body, you have a very huge surface around it, and you see that there is a region in which there is a less amount of fluid coming through this, and it does not depend on the size of the radius of the surface. What it tells me about a potential flow outside of the wake. Let me remind you what was a potential flow before Prandtl. You wanted to say something? Absolutely right. There must be a flow excess compensating for this deficit. Namely, through all this region, we need to have a flow because it's an incompressible fluid, right? So it's the amount of fluid inside the area does not change, which means that if this is independent on the radius of this huge sphere, then this must be independent, the total flux. But its area grows, we don't know how this area behaves, but it's a tiny part of it. So this is all grows like r squared, right? R now is a distance from the body. What it tells me how velocity must decay with the distance? Potential velocity outside of the wake. 1 over r squared. It tells me that my V perturbation must behave as 1 over r squared. Let's exhale. And what did we learn before when we discussed potential solution in the first lecture? We say, look, it's a body, it moves with the U. All solution of Laplace equation is 1 over r, grad over r, and this. It's a four potential. Then velocity here would be 1 over r squared. This would be 1 over r cubed. And we, of course, said, of course, we need to take this, right? Because it's a dipole field. Why we did not take that? Because it would produce 1 over r squared, which is like a charge. It's like by Gaussian, it produces a net flux. Now we need to take it because it needs to compensate this wake. That's singular perturbation in its maximal beauty. I really want you to appreciate it. What means singular perturbation? No. A force expressed in terms of this deficit. Force acting on a body does not depend where I put my surface to compute the deficit of momentum. That's easy part. So now, again, let me remind what we are doing. We're turning nu into 0. And it's a derivative in front, and it's a factor in front of the highest derivative. That's what mathematicians call singular perturbation. Because when we added this Laplace term to the Euler equation and turn them into Navier-Stokes equation, and somebody reminded me that we have 100 years since Navier, so we're celebrating also centenary of Navier equations. When the factor here, when we added second order term, we also needed to change boundary condition because we raise the order of our differential operator, we need extra boundary condition. Turning into 0 factor in front of the highest derivative is always very dangerous procedure. And now we see how it, and it works differently in different kinds of singular perturbation. Now we see how it works here. What we learn from Prandtl that this single perturbation create very small, tiny boundary layer. But because the system is nonlinear, we have this pressure, high pressure low. It's all manifestation of nonlinearity of a fluid motion. This tiny boundary layer is getting detached, propagate up to infinity or until we buzz to measure, and change the flow in the rest of the space. That's your singular perturbation. I really want you to appreciate the power of a small factor in front of a highest derivative. It flows not only behind in the wake, but in front too. Right? That's a stationary flow. Of course, it's this change is kind of smaller here and it's larger here, but it's 1 over r squared term. Yes. Why do we care about force? Cost money. You know, you drive your car, it costs a lot of money, and it's all you spent driving your car is this force. Trust me. Okay? Good. No, you know, this V is a correction to U. The main thing is U. Very far from a body, everything moves almost with U. This V is a small correction to it.
That thing that you, the wake and separation, that's behind the particle.
That's behind the body. That's behind the body.
Behind the body.
Yeah, flow, sorry, it's not very visible. Flow comes from the left and then moves to the right. And then, you may say that this is my body. It moves to the left and wakes is behind, okay? And now, so really, I want again to repeat this statement that there's no mathematics here. It's kind of hand waving. Oh, if you look into the book, there is still some very subtle argument how you need to argue that the really diffusion of momentum behaves this way or that way, but it's essentially a very simple argument. It's really that whatever small viscosity, there is always a tiny layer in which it is important. In this layer, you produce vorticity. This vorticity cannot stay near the body no matter what its shape. When we do a wing of an airplane, it has a very streamlined form, so that it's really a fluid particle come like this and live really very kind of close, and still there is a wake here. And this is the region of rotational flow. This is where vorticity is not zero, and that allows for forces. And it changes flow everywhere. That's what is important. Personally, I find the most surprising part this one over R squared. This I remember when I first learned it, I said, wow, it could not be. It's just this tiny boundary layer. Okay, so it's left behind in the wake. Okay, so there is somebody behind me would know about it, but it changes also across. It changes flow everywhere. Okay, and now what Julia suggested that we do, let's now trace our way from Stokes flow to Prandtl flow. How we get to such a dramatic thing? So let's again start from this very low Reynolds number. Absolutely, yeah.
Can you tell us the number? You know, what ratio? Where does that separation occur and then you go to zero?
That's precisely what I'm now going to tell you. But let's start from a Reynolds number very small, and then as we increase Reynolds number, you'll learn where it happens. Okay. So now we start from this Stokes flow, and now I want you to which
You went from 1 over R squared to there's miracles. But how does that 1 over R squared feed into the finite force?
Oh no, it's not a finite force. A finite force is a width of a wake. That's it. And what I say is that as long as you have wake, you have a force. What I told you is the next thing. So this 1 over R squared and the fact that I changed my flow outside of the wake has nothing to do with the force. Force only comes, it's the potential part. It's 1 over R which gives it. So flow outside the wake is potential. It gives no forces. But it's a potential flow different from what you expected. It's not a dipole, it's a charge potential flow.
Where does the factor of vorticity in that way give you the right answer? What step is
No. The fact that vorticity in the wake over here makes this integral non-zero of the wake area. So the fact that I don't have potential flow makes this integral non-zero and provides for a finite force. And I did not compute it. I just argued that the wake now removes paradoxes. Okay? And now I know that actually the force, resistance force, is essentially wake area. Okay? And now, but it also, what is important here, the most important thing that I believe, is that it's a deficit of a fluid flow through the wake area. And because it determines the force, I'm repeating my argument, but it's important enough, right? That the deficit of a flow is independent on the position where I take it. And that means that all the rest of the flow, even though it's potential, must be all 1 over R squared and not 1 over R cubed, as we thought before. Questions? Yeah. Okay, good. So now let's try to connect the Stokes flow at a very low Reynolds number to this wake flow at a very high Reynolds number, and ask where it actually happens. And what I now want to do with you together to look at it is something which you can find in any engineering textbook. It's a flow transformation with Reynolds number, but I want you to look at it as physicists. And physicists are curious people. They're mostly interested in symmetries in their breaking. For some mysterious reasons, it's yeah, probably not. So Reynolds number very small. We have the Stokes flow, which Julia have shown you. It's a Laplacian 1 over r is equal to delta function. So your velocity is 1 over r. Let me ask you which symmetry it has. Because now we'll be raising Reynolds number and breaking them. So let's list what symmetries do we have of a flow. Huh? Left, right. Is it an exact symmetry here? Only in the limit of 0 Reynolds number. It's actually left-right symmetry is O of real. You can always compute the next correction and see that it's a little bit different here. It's not vague. There is no kind of recirculating vortex, but it's a little bit asymmetric. So it's an approximate symmetry. Are there exact symmetries? Huh? It's axisymmetric. Or if it's cylinder, it's up-down. Okay. So let's say up-down. Good. What else? Yes, very good. It's natural to forget about time, but in the moment we understand that we raise Reynolds number and it starts fluctuating. So we lose its symmetry. And before we lose something, we better get accounts of what we have before we lose it, right? So it's time translation. These are two exact symmetries. This is approximate symmetry. These symmetries are exact even at a finite, small but finite Reynolds number. This symmetry is approximate. Okay. Now we won't be deriving this. I will be telling you what nature does. And most of it we still cannot derive. We measure it with very high accuracy. And you're welcome to try to derive some of them because some of them probably derivable. So Leo, answering your question, what happens at Re of order 4? Wake appears. That's what happened. Not at Reynolds 10 to 6. Well, this is very small. Let's make the next picture, which would be that's a wake appearance. It's very tiny. Still, it's already, it definitely changes left to right, but it was not exact symmetry. So what did change here? What is a qualitative change from here to here at the rear of order 4? For sphere, it's probably 5. The cylinder is 4. What qualitative change happened? Yes, we introduced vorticity. You may say that we have a potential flow. Now the flow, there is a region where it's non-potential. But as any physicist, particularly condensed matter, people would immediately tell you that what changed here is the topology of a flow. That's a qualitative change. We did not have closed streamlines. You know, this Nature article we are so proud of is that we found closed loop streamlines for electrons in graphene. So this is indeed topological change. Here, all the streamlines go from left to right. Here there are streamlines which are over there. Can you guess what would be the next change around 40? Yes. Yeah. Okay. Anyway, I cannot let professors not to talk. We are losing at last the first loss of a true symmetry. We lose time translation, and you imagine how, which means that some things start to happen in time. And what happened? Huh? Yes, absolutely. So what happens is that the flow is not, what means increasing Reynolds number? It's always space because we don't change the size of the body. Think of it as increasing velocity, right? Which means we increase velocity. For these vortices, they just don't have enough time to recirculate properly until flow passes it. And they start to detach. Now, when they start to detach, they detach not simultaneously because it's difficult. You need to break also this symmetry. So what you've got outside, yep, where is my, oh, I'll,
Quick question. So Reynolds number 4, that's something you can sort of derive analytically?
no, no. That's, you know, the most frustrating part of it. You know, when I was like most kids here, I thought that all hydrodynamic transition happened like at Reynolds number like 40. So, yeah, good. 40 is a big number. 1/40 is a small number. There's probably some kind of a hidden small parameter over there, which I will use and then solve it. But 4, for God's sake, I mean, what you can do with the parameter 4? Just look at the Navier-Stokes equation. Where is this 4 number is hidden there? Anyway, so what happens is that behind your body, you would have this type of vortices. Okay, so vortices start to detach one by one. Yes, Julia?
Start tiny and grow. Is it a continuous thing, or do they just?
They actually grow as they grow downstream. If you go a little bit further, you would see that your wake is getting like this, and there is tiny vortex here and larger vortex here, and there is tiny one. Or if you go from 4 to 6, of course, it's grow. Yeah, this region, yeah, if it goes down to 4, it actually shrinks, but it shrinks to a finite size. They are not infinitesimal. Yeah, it's probably like first order condition, yeah. But again, just let me add this. But it's not really a phase transition because we aren't breaking through symmetry. There were no left-right symmetry before. We were just changing topology. So if it's phase transition, so it's something which you need to think a little bit differently. It's a topological transition. But it's a jump. Yeah, absolutely. Okay.
Is this the same way that qualitatively you see in the airplane wing?
That's exactly the same wake which I produce now by my tongue. Yeah. Well, it's a wire singing on a wind, you know, or behind. Airplane wing produces this stuff with vortices. Absolutely this stuff. Yeah. And there is a funny story. I mean, von Karman, and of course, you know, this is called von Karman Street. And von Karman is the guy who actually created a lot of aircraft industry in this country. He was a PhD student of Prandtl. I mean, everything, of course, kind of closely connected. And they were measuring, Prandtl was measuring with his technical assistant, a resistance of a cylinder in a flow. And they measured it and it kind of oscillated. And they said, yeah, it's an imperfect cylinder. Let's polish it to make it a little bit more perfect. And von Karman in his memoirs says that every morning he came to the lab and asked this assistant who was every day polishing the cylinder better and better. And he asked how, and he said, still oscillating, but I will polish it more. And then von Karman actually understood what's going on. That no matter how you polish your cylinder. So here we broke time translation and up-down symmetry simultaneously. But, yes? Huh? No. Time symmetry means it's a steady flow. That's it. Time translation symmetry. Look, let's be accurate. It's a continuous group of time translation by arbitrary time. We broke it, but not completely. You know, we like our symmetries. We cling to it. So what is left out of breaking two symmetries? One was discrete, up, down. Another was continuous, time shift. We break them together, but we actually replace them by a single symmetry, which is Yes, excellent. We replaced it by a combined symmetry by shifting of a period of shedding next vortex and simultaneously replacing up and down. Because vortices shed one by one. So if you shift by this time by which next vortex is shed, it will be vortex which is down. You see the beauty of it. So, and it's very often, it's a very important lesson here that very often when you break continuous symmetry and you have another discrete symmetry present, that what you get a combined symmetry, which is now discrete. Okay, it's a discrete time shift and up and down. And then what happens is that, as it says in the Bible, in the original language, tohu v'bohu. It's a primordial chaos. So it's go further and further away. Vortex is getting clutch and then it's getting turbulent. Okay. And now, what I want to spend the last half an hour is to look inside the wave and to tell you how this anomaly of having constant resistance at the limit of zero viscosity produce dissipative anomaly, namely having a constant dissipation rate inside turbulence when viscosity going to zero. Okay? Before doing this, questions about body, wake, anomaly? Yes? Absolutely. It's a stationary flow. It just has topology of closed streamlines. It's not moving. Yeah, no, it's just they are circulating because it's still a slow flow. They have enough time to circulate. What happens when you increase velocity, the vortex don't have enough, and it has a complicated structure. And I don't think anybody would analytically describe it. I would think that, you know, as a very transition, you would get something which would be approximately circular or approximately very, very like Kelvin cat eyes. No, I never found any decent analytic start point for this. Okay. Question. Speak louder. Yes. The question was, what is this V which I so blazingly wrote here? Well, it's U is a constant and V is a function of X, Y, and T, and it's mostly negative inside wake. Namely, that velocity inside wake is a little bit less than U. That's what created this force over here. Right? So it is just a perturbation. But the point is that this perturbation is something which is not described by potential flow when if you are inside the wake. More questions? Yes. Speak a little bit louder. I'm not sure. Good question. No, it actually comes in the Reynolds number. We don't need infinite Reynolds number for it. Okay. Essentially, where it would be, where you will see this 1 over r squared, where you have your wake already producing a finite deficit, there you would need a compensating reflux, which is 1 over r squared. So for Reynolds number 4, you still don't have any noticeable deficit far away from the body because your wake shrinks. Over here, your wake starts expanding. And that's what creates this 1 over r squared flow. So I think the tiny flow would start, tiny 1 over r squared flow already will be noticed in Reynolds number over 40. But for this, you need expanding wake. And I probably won't have time to derive the law of expansion of the wake. Okay. More questions? Yes. No. Here, V is 0. Here, U is, V goes to 0 at the right, and it goes to 0 at the left. But at the left, it's exactly 0, kind of like everywhere, until you hit the, well, okay, it's a little perturbation, but here it decays like 1 over r squared. And here it defends much, much slower, and I won't derive. Well, maybe I will see how much time I would have. Question.
I was wondering if, do you think the result of the dissipation anomaly would be independent
kind of stress density and like instead of viscosity?
Good question.
I'm thinking of specifically
Good question.
fluid where you take the coherent limit that the coherence thing.
Yeah. So the question was that we have a particular case, we consider particular case of singular perturbation, new Laplace. Imagine I would do new Laplace squared. Or as quantum mechanical people would have it, I would have a perturbation which would be EH bar Laplace. Incidentally, as you probably noticed in Srini lecture, the quantum of circulation has the same dimensionality as a vorticity. Because as we say, vorticity is some velocity times some scale, and it's circulation, right? So, and it's, where is Leo? Leo advisor Paul Wigman always say, well, our quantum mechanics is like your viscosity. It's essentially small factor in front of a Laplacian. Well, it is not, because, you know, a Schrödinger equation, ddt is I Laplacian, not Laplacian. And people who say, well, quantum anomalies are like your viscous anomalies, it's a very interesting question for which I don't know general answer. What I do know is that if I take Laplace squared there, for example, many things change, but something would stay. Finite dissipation would probably stay, but there will be very different laws. Changing nu into imaginary nu, or doing analytic continuation in this, what we like so much like doing, I don't know. I don't know. It's a good question. Okay. If, yeah, last question, and then we go to turbulence, because you want to know about turbulence, no?
Why does breaking upright symmetry by only a small amount not produce an anomaly the same way breaking time symmetry by a small amount?
To produce anomaly, you need to change flow in the whole space. That's the dramatism of it, okay? That's what produces anomaly. And tiny perturbation change a flow in a little region. Or it produces these vortices, and you change topology. It's not yet anomaly. Anomaly is this, going all the way to infinity, namely starting to expand. For this, you need to break time translation symmetry. It's a really dramatic change, right? And of course, anomaly appears only in the limit, because again, anomaly is when viscosity disappears, viscous resistance stays finite. To do it is to have it in the whole space. But now let me show you another way to have finite effect of infinitely small viscosity without having anything infinite in space. Okay, and this is called now not a friction or force anomaly, it will call dissipative anomaly. Okay, good. So now when I want to look inside this wake and say, look, and I would rather, you know, I don't want this infinite wakes, etc. So let's say I would have my enclosed space, the fluid, and I would have some kind of a propeller rotating inside it, right? It would have its U, it would have its R, it would have its Reynolds number, U, R over nu, and I would want it to be in the infinity. And what I know that I need some constant force to rotate this propeller, even when nu goes to 0, right? So my force actually stays finite. And it, let me remind you, is C U squared R squared rho, that's my force, okay? I want to now say, okay, I put all this power over there. Let's take this force, multiply it by U, that would be power, right? And I would definitely heat the air inside, right? Okay, so let me use my air condition. So I will take heat away, I will keep a constant temperature, okay? So I have a steady state. I have a constant temperature, I need heat taken out. But what I'm actually claiming is that when nu goes to 0, when Reynolds number goes to infinity, this power rated a limit. Let's take it over the per unit mass. So I took density multiplied by volume. That's my power per unit mass. It's the energy dissipated per unit mass. That's how much my air condition need to work, right? Which is, it's called epsilon, and it's U cubed over R. And there is no infinite wakes, nothing about it. It's just having some turbo. Apparently, I create vortices, etc. And then we ask how the hell here it happened that we have a dissipation amount of heat released per unit mass independent on viscosity, even though viscosity is what produces this heat, right? And understanding of this phenomenon surprisingly started very far from it. It started from Richardson, who probably did some totally different things. He released balloons in the air. I think you also did this when you were kids, or sometimes unintentionally. He did it intentionally. He released balloons in the air. Sometimes he released some seeds, anything that would fly for some distance. And what he did, he measured distance. So you just take two balloons, or you release them after some time. So you just measure a distance between them. Let me also call it r at time 0. Then they follow their whatever strange trajectory. And at some point, you measure distance at a time t. 1926. Okay. Actually, 1924 was the experiment, but application was 1926. And what do you expect? It's kind of a random process. What do you expect r squared to behave this time? It grows on average. How we would expect it to grow? Linearly, if you would be thinking about diffusion, and diffusion was all the rage of the day, you probably know, Einstein did his work on Brownian motion. People actually measured the size of the atom by measuring, this Perrin and other people in Europe. So everybody expected linear growth because diffusion is more or less what you expect. You do some random steps, and if you average over time, which is much larger than the typical time of your step, you would expect t. He got t cube. Very good data. And now in the lab, we're trying to have this t cube, and it's cost a lot of money. What would be the dimensionality of a factor standing between centimeters squared and seconds cubed? It will be centimeters squared per seconds cube. What's the relation, right? But Richardson understood that there is something, well, let's provisionally put a question mark here, but it's definitely centimeters squared per seconds cube. And he then argued as follows. He says that what that law would mean, why it's faster than diffusion, what's the physics behind it? It tells you that the more you separate, the faster you separate. Diffusion is essentially a uniform process of separation. No matter what you are the distance, you add the same amounts, okay? What we call now Richardson diffusion or turbulent diffusion or super diffusion, it's something which tells you that the further away you are, the faster you separate. What kind of a physical mechanism would be responsible for it? Let's make our fantasies about it. Why? Why there's two balloons separate? Because they have different velocities. Right? There is no molecular motion. They're big balloons, well, like this. They're big balloons. They don't care about molecules. They care about wind. So wind is here like this. Wind is here like that. So why the hell the difference in velocity between 2 points depends on on average, depends on the distance of the points, and the further away a point, the larger is the velocity difference. Because there are vortices. Imagine that you have vortices of different sizes. If you have 2 points over here and you have vortex like this, it would not produce noticeable notion of this with respect to that, right? And if you have a big vortex of this scale, it would just transport them simultaneously, right? So to provide separation between the points, you need vortex like this, and that would move up, this would move down, and you would see separation, right? Would have different. So essentially what it tells us that there is this motion which contains many vortices, and somehow the larger the size of the vortex, the more energy it has. Let's estimate. So essentially what Richardson said, probably I'll go towards a new page. So essentially, well, it's a pity to erase it, but I was advised to leave for a while all my, so that you can meditate looking at it, but it's probably enough meditation on the wake. So if you're interested in R of t, right? And you know that the solution is RT3/2. What would be dr dt, right? It would be T1/2, right? But, or in other ways, it would be R1/3, right? But yet, on the other hand, it's delta V on the scale R. Richardson argument was that to have Richardson diffusion, you need on average that the velocity, kind of mean velocity on a scale R scales like R in 1/3. And that produced one of the most interesting ideas in physics of 20th century, the idea of a cascade. Try to imagine what, I already gave you a name. Name already 80% of the idea. So how would you have this cascade coming out of delta V proportional to R1/3? Actually, Kolmogorov derived the cascade practically without any knowledge. Obukhov knew, but Kolmogorov did not pay much attention. So what would be the idea of a cascade? Cascade of energy. How would you imagine? You've heard about it, right? So somebody volunteers to give it in one sentence definition. Huh? Speak louder. Is it something about time or about space? First of all, cascade in time or in the scales? In scales. Aha. So the idea is that you create these big vortices. For example, you drive your car, which is, as we learned, not for free. So you satisfy Prandtl condition on burning enough fuel. You leave behind big vortices. Viscosity is so small, these big vortices just have a Reynolds number like 10 to 5. But they can break it smaller vortices. They can break it even smaller vortices. They can produce even smaller vortices, which all are inviscid. They don't dissipate practically. But eventually, they can produce a very tiny vortices where Reynolds number will be for the unity, and they would dissipate energy. So that was the idea of a cascade. And for it to work, you need to say how much energy per unit mass, which means that everything will be per unit mass, you have if you have a delta V of vortex of this size. Well, you see that energy is more or less delta V squared. That's how much energy you would have at delta V on a scale R, right? Now, if you really have this cascade idea, you must say the following. It does not matter on what scale am I, on this scale, on that scale, or of that scale. They all don't dissipate. They dissipate only on this tiny scale. So what they do, they just transfer energy to smaller and smaller scales, which means that my rate of energy transfer must be scale independent. But rate of energy transferred is dimensionally, some energy divided by some time. What is the typical time that can be associated to motion of the vortex of the size R, for which velocity is approximately delta V? Circulation. I mean, fluid mechanics is what is beautiful. That every time is distance divided by velocity. Everything. So we say that what is here some time must be delta V squared, some R divided by delta V. And that's delta V cube divided by R, and we want it to be epsilon. Okay? that's maybe one of the, well, this is definitely the most important formula of turbulence, and we, in all our years, did not produce much comparable to it. Kolmogorov actually derived it as a third moment average. You can do and derive it, but the physics is quite clear here, right? So this statement, the delta V scales like R over in the power of 1/3, is essentially the statement of a cascade. And it tells you why is the energy dissipation rate is independent of viscosity. Because this cascade acts like a pipe. If you look at this at K space, where K is 1 over R loosely, so you put somewhere your energy over here, and it goes, and here viscosity stops it somewhere, when a Reynolds number would be for the unity. You decrease viscosity, it stops it further. It's the same flux which goes there. Okay, so decreasing viscosity, you increase the length of your cascade, but not the amount of energy flow which goes through it and which is eventually dissipated over there. Okay, this is what now physicists call dissipative anomaly. Because if you look at this quantity, it essentially says, and what Kolmogorov derived, called fourth law, is, let me give you now a little bit more accurate mathematical definition. Is that if you take 2 points inside the turbulent flow, you measure velocity here, which is a function of time. You measure velocity there at 2.1, 0.2, which is also a function of time. It's a vector, here and here. So let's make the difference, which is delta V. It's a vector. Let's project it on this direction. So let's call it delta VL. So the statement is delta VL cube mean value is epsilon times R12 minus 4 over 5. You can derive. It is delta V cube divided by R proportional to epsilon, but it gives you factor, it gives you size. In 2D, there will be plus 4/3. I won't now go into this much. What I really want you to show is that this is a symmetry breaking here in this formula. Which symmetry breaks this formula? Delta V cube equal to something. Which symmetry third moment of velocity, non-zero third moment of velocity breaks? Huh? Of course. When you reverse time, V goes to minus V. So if you have a time reversal statistics, as you would have in equilibrium, by the way, no matter what kind of dissipative or non-dissipative, you have a detailed balance which tells you that your statistic is time reversible. Probability of going here is the same as going here. No, this is, it breaks time reversibility. What breaks time reversibility in the equation? Of course, nu Laplace V. But this is the limit of nu going to 0. 0. That's why it's called anomaly. So symmetry breaking factor nu goes to 0. Effect of symmetry breaking stays finite. Okay? It really means the following very quite simple statement. You take a movie of turbulence, you show it. It actually was written in our review with Srinivasan. You show it to expert, means to Srinivasan or to Falkovich, and they will tell you if you screen this movie rightly or you just screened it back in time. The vortices, going like this, like this. I'll look at this movie, I'll do statistical average, say, no, this is the wrong direction of screening movie, okay? Even though viscosity is tiny. So this is really what I believe is a second lesson which we can learn out of fluid mechanics, is that it's has its singular limit of viscosity going to 0. We happen to live in a world where most viscosities aren't very important. Again, let just as a last thing to have you a little bit of everyday feeling of it. Nu is 0.1 centimeter squared per second for water, and nu is 0.15 centimeters squared per second for air. By the way, what it tells us, what is more diffusive kinematically? So you create a vortex of the size r, or you move a body, and the typical time of diffusion is r squared over nu, right? So the same vortex would live 15 times longer in water than in the air. Water is actually less viscous fluid than the air, kinematically. Forces, of course, are very different. But if you take this, for example, air, this 0.15, and consider any cloud with a wind which is like 10 meters per second and a scale is like 10 kilometers, it would give you 10 to 6, 10 to 7 Reynolds number. You drive your car, you have 10 to 5, 10 to 6 Reynolds number. So we live in a world of very large Reynolds number mostly. And that's why we find it, first of all, so important and then also so surprising. Okay, so I really wanted to leave last 10 minutes for questions. So let's have questions, and if not, then I might be at few words. Yes. Question was, how would I distinguish, or Srinivasan for that matter, looking at the movie? Of course, not dynamically, statistically. What I would do, looking at this formula, I would look the following. I would take 2 points and measure this velocity difference, delta V, as a function of time. What I expect it to be averaged to 0. On average, there is no preferred direction, neither this way nor this way. I just randomly pick 2 points. So I expect this delta V to be 0. That's okay. But then I would expect delta V cube to be negative. It means that every time I see stronger velocity difference, it rather be in this direction. Why in 2D it's opposite? If in 2D I see large velocity difference, it is in that direction. Try to guess. Yes. Huh? Who said inverse cascade? Good. Inverse cascade means energy goes to large scale. Direct cascade means energy goes to small scales. You have big velocity difference and it's mostly negative, means that this big energy would go to smaller vortex. In 2D, it's positive, which means this big energy would go to larger vortex. Okay? That's the difference. Okay? So that's how I would distinguish it. Yes. Which picture? Absolutely. There is no difference between, you see, the moment that I am saying is that the rate of energy transfer must be the same through scales, it applies to 2D and 3D because there is nothing about direction. Okay? In 2D, it will be direction from small scales to large. In 3D, it will be from large scale to small, but the statement that the transfer rate is independent on scale is the same. So it works in 2D and in 3D. Yeah. Energy goes to larger scales. Yes, that's true. Okay. More questions?
On your phase transition, is it hysteretic? Well, I guess you've erased it now. But if I now go from 4.2 Reynolds number down towards,
yeah, probably it
disappears. It goes back to
it's a good question. I actually did not remember seeing the data, but it's most likely hysteretic. Yeah, that's true. Mm-hmm. Okay. Yes.
And also with symmetry breaking, and also like quantum anomaly, it's also like singular perturbation on like the third Navier to square power, and also there's also
let me rephrase the question, because you very kind of suddenly put all the eggs in the same basket, and which means that we look at anomaly. Again, anomaly is that symmetry breaking effect stays fine at symmetry breaking. From the viewpoint of, like changing flow in the space. We can also look at it from the viewpoint of having singular perturbation in the differential equation. Or we can look at it from viewpoint, like, for example, in quantum field theory, when you have chiral anomaly, if you don't know what it is, don't matter. We have two symmetries kind of contradicting each other. So in a sense, you may say, okay, I have this symmetry, I have that symmetry, and if I consider whatever, some physical mechanism, they contradict, I need to sacrifice one of them. So there are very different ways of having anomalies, and it would be nice somehow to put them together. And maybe Polakov can do it. And every time I ask him, so Sasha, you can just like in half an hour, like explain everything to me in a very compact form so that I can say, okay, I say, well, okay, let me start. And after 3 hours, we understand that it's actually much more complicated. So what at the moment I'm myself working on it, and some of my students, I'm trying to sort it out from the viewpoint of entropy and information theory, because the dissipative anomaly, I think, is different from chiral anomaly, in the sense that in this anomaly, you dissipate finite amount of energy per unit mass, which means that you dissipate a finite amount of entropy. In chiral anomaly, I see this as zero entropy. So they are different, but they are related. How? That's precisely what many people now are working on. And there are anomaly in Anderson localization, and there is anomaly in having the finite resistance of a medium in which there are only elastic scatterers. There are many anomalies in physics. And it seems like last 10, maybe 15 years that the interest grows. That's why I've decided to tell you. I know many things about fluid mechanics, right? But I wanted to tell you this because this is something which is very hot right now. And we are very far from any understanding of it. Yes.
For the time translation breaking, or as someone who can ask, I think if there's continuous translation breaking, there's a gold stone.
Yes.
Is there an equivalent mode that exists in mechanics?
Well, Goldstone mode is actually related to the space translation. So you have something like a sound mode, which means omega goes to 0 when k goes to 0 if you really have a kind of a continuous limit. No, I don't think there is the mode related to it. There are some situations, but it would probably will be more like a contained flow, like a flow in a pipe, and the way it breaks. And I didn't tell you anything about how actually turbulence appears. There are two ways, and we didn't talk about it. It could be that in a contained flow, like in a pipe, there are some modes. Nobody did any decent physics about it so far. Yes. Huh?
For the Richardson experiment, when was that relation? Like, I'm just imagining if the weather was very extreme.
Tens of yeah. So the question was, it's Richardson experiment, on what scales it works? Because when there are a few miles between your balloons, it's very difficult to observe it in 1922. The real measurement started more or less on a scale of a meter or half a meter. That's where you start. And most of the data was tens of meters. And it was very, very ingenious way to measure such distances. And when they go further away, you don't. Now in laboratory experiments, we have 3-4 orders of magnitude. And it's not very easy because it's a lot of things to control. But you do see T cube. Yeah. And I even once computed the coefficient in front, but it was still probably in 2D basically. In 2D, you would have the same law, but with a different factor. Yes. Okay. And now for the best part of it, yeah, I really want you still. I mean, a few first questions, and if you want, I will sign it. You can take it. Let's just shake hands. Okay, good. And that was also a very good question. So let's smile. And the third, I need to call from my list. Let me Just, yes. This is Samar Algatari, right? Where are you? Yeah, okay, good. Let's make this your let's make this your picture. Yeah, I was actually nearby. Okay, again, that was first lecture, I guess. Wait. Done? Done. Good. Thank you. Okay, thanks to all of you. I had an enormously good time. Good. Break.
After dinner, please come back to this room and we'll have a kind of list for spoken advertisements for the 17 poster. And then starting at 7 on 11.
Oh, 11th floor of which building? And where it is?
It's just down the hall. But I need to go,
You mean I need to go outside? Oh, okay. Mhm. Uh-huh. Mhm. Mhm. Okay.